today's topic is I would say the second part of the data visualization part of this lectures. It's about viewing relationships. How can you determine relationships between variables, and why would you want to do that? We will take a look at those in this lecture. So why do you want to know relationships? As we know from the last time that we want to know distribution in data because you want to determine whether the data are normally distributed, whether they are outliers, whether there are multiple populations in the data. Because once we know that, we can clean the data, we can separate them out, we can clean outlier, we can calculate significant representations, the representations of the data that can be used to determine maybe the difference between groups, or you can use them to use them to make you understand the data more. Now, that is for one variable, right? If you have multiple variables, if you have two columns of data, what would you do? Right? The two columns of data that looks like, for example, on this left-hand side here. You have one column as age group, one column as subject ID, and one column as sex. Now, from this, usually some people may have there are something like a rule of thumb. One rule of thumb that I have learned when I work with real data is that you shouldn't use the ID to do any calculation, and you need to be careful as well when you're creating a model to exclude the subject ID or the IDs out if those ID representing each unit of analysis that you are doing. Right? If the IDs are, for example, province ID, the ID of province, and you want to use province information, province data, then it is fine to represent the ID as, for example, we will learn about that later on, as the one hot encoding of that numbers. But for some ID like customer ID, account ID, or row ID, the IDs that represent the primary key, the keys of the row, those IDs are actually useless because they represent nothing. You cannot, you can use them for counting at least. If you want to count a unique ID, that is fine. But if you want to use them as variables, it is not representative of certain characteristic of the data. So it's not good to use such an ID columns as variable that you want to use to analyze data, right? So what do we have here? We have two columns, age group and sex. If when we have two columns together, what would we want with these two columns, right? Each column can be analyzed using one variable, using univariate analysis to determine distributions, to determine the center. For this one, well, some of you guys ask me, how do we determine the modalities or the distribution or the center of category called variables? Well, think about it simply in this term that you have categories, you can count them, right? Then the majority or the center of this distribution can then be represented as the mode of the values, right? The highest number of count or the second highest, those high number of count. Those numbers will tell you which category would appear more often than other categories. And that is the way that you can analyze them by simply counting the frequencies, counting occurrence of these values. But those are for univariate again. For the two variables or the bivariate analysis here, the thing that you want to determine would be relationships between columns, would be the associations of, for this one, age group to sex. right? Whether they are dependent of one another or independent of one another. You may have learned this already, this concept of independence and dependency, right? In your statistic class, that some variable may depend on another variables, numerical variables. Their dependence would appear, well, if they are, if we represent the probability of these two events, the having this S group and sex, and then if they are independent, then there will be certain characteristics in probability, right? You have learned that in stats class, I suppose. So how do we determine the dependency of these two columns? One way to do that, now I'm going to iterate through the type of variables that we can encounter, starting from if you have categorical variables versus another categorical variable, right? What would we do in this case? And then categorical and numeric, and then numeric and numeric. Right? So let's start with this categorical versus categorical variables. One way that we can represent this relationship is to transform the table from this format, right, or from the long format or the transactional format on the left hand side here, into this cross tabulation format. In the cross tabulation format, you will have one variable as an axis in one axis, and another in another axis. For this one, S group is now used as axis for the rows, and sex is now used as axis for columns. And then the values or the number inside here represent the count of each of the combination. So for young female here, so we have this the first row here, young female, young F, and here JT, young F, right? And by counting them, right, you have this occurrence, is this count out. And this table represents the joint distribution between the two variables. And when we count the number of occurrence, the total number of occurrence, this is equaling 11. If we use 11 to normalize, to divide all the values here, now you get the joint probability distribution of this empirical distribution. So by converting from the transactional way here into the cross tabulation, you can now determine association between age group and sex, between the two columns. Okay. So how do we create this in R? I'm going to show you the way that you can analyze, and then the code that would allow you to do that, and demonstrate it in the actual code. Okay, you can use the function called table, and it will generate the cross tabulation between two variables. But for now, I'm going to import the data in here, the bank data.csv. Well, let me use tidyverse first and read the data in. Well, use the F then. And then click run. Now you have the DF here. And way to determine that is to view it first, that okay, looks fine. And then let's create a table, the cross tabulation. You can use function table. And table, if you want to know how it works, not Google them though, help, right? You can use help the help function here, or you can just search here, table. It will show you the table. There are many of them here. maybe a better way is to just use this here, and you find it in the base cross tabulation and table creation. The function table. The function table require you to put in the here, triple dot here, one or more object which can be interpreted as factor or a list, right? Then it will use those to create the table for you. So for this one, I'm going to use df marital and whether this marital and y. df dot sign and y, right? And when I run this, so this is suppose that I might want to know whether marital status associated with the chance of customer accepting the offer or not. Then viewing cross tabulation would allow me to determine association between the variables. If they are associated, then it will indicate that we might be able to use marital as a marker, as an indicator to identify those who may want or who may not want to accept the offer before we actually begins or before we do the task. Right? This is like trying to predicting the future, that you are trying to find the keys that will lead you to the correct answer, the keys that associate with the event that might occur in the future. Okay, running this, now you get the table here. This is the cross tabulation. You have the number of occurrence of divorce and no, divorce and yes, married and no, married and yes, and single and no, and single and yes. Okay, this is the way that you can create cross tabulation. And from this cross tabulation, you can then perform further analysis. All right, how do we perform that analysis? There will be slides about that later on to determine using chi-square statistics and also to determine using the conditional probabilities. But let's wait. Let's look at the way that we can plot this into graph first. Right? How can you represent this instead of as a table into a graph? To represent the relationship between two variables, there are, well, multiple ways that you can do that. One way is to use frequency table as or the cross tabulation. The frequency table is just for one variables. The cross tabulation to representing the two variables, right? Another way is to use graphics. There are also multiple choices to use in the graphics to represent association. The one that I show you here is the use of bar chart. When you use bar chart, you can represent the association as the stack bar chart. In the stack bar chart, will show the high here is the cumulative, is the combination, the sum of both yes and no here in each marital status. So if you just remove the field equal y out, then you get exactly the same bar chart, except there would be no color, right? The division here can be thought of as partitioning, that once you introduce the field equal y into the graph, then this ggplot2 use the y here, which has the value of yes and no, to partition data into parts, and then put those parts as a separate data object to represent in the graph. In this case, we have no to be in orange, or what should I call this color? Salmon color? The red tint, I don't know, the red color, right? And this again should be green, right? Someone view it as blue, should be green, right? The green color is yes here, and you see proportion all together with the height. This graph is good in viewing the amount, and well, in viewing the amount, and at the same time seeing proportion. But this graph might not be suitable if you want to compare across the category to see if they are related or not. The reason is that if you look at this one, you may thought that this has like a very small proportion, but it might not be the case, because if you were to stretch the whole bar up to be equal to, say, the merit amount here, then it is possible that this would be larger, which we don't know, right, for now with this graph. In any case, let's start with the stack bar chart first. Right? What I'm going to do is to use ggplot, doing the same thing as in that with df, and then map aesthetic of x to be equal. I used Yom bar, right? So x should be marital, and then plus Tom bar. Without fill equal y, and we got this graph. Right? And once we assign fill to y, then we have the stack bar chart. Now, the stack bar chart can be arranged in different ways. So instead of viewing it as an absolute value, the actual count of occurrence, you can scale the y-axis, right, to 0 and 1, which that scaling will result in the change of the stack bar chart into the stack bar chart, the fill stack bar chart. That is, it will scale everything to 100%. And with this, it allows you to compare proportion, right? Because once you scale it here, it is like you are determining the proportion just in that specific category, and then trying to compare the specific category across the multiple levels. Right. This is called the fill stack bar chart. And it is used to compare proportion, whether they are the same or not, because the proportion indicates the chance. The chance indicates the likelihood that the thing will happen if you have certain status here. Right? For this one, it indicates the probability that customers would say yes if they have certain marital status. Right? You can know that beforehand. Right? Now you are like an astrologer, trying to observe things and then predicting futures. Okay, so this can be done easily by using the position equal fill. And you got the stack bar chart. But for this one, it shows you that, well, in terms of the proportion, they are not that different though, because in terms of the level here, they are all about, let's say, 13%. Yeah, they are about the same, 13% for divorce, for married, for single, about 13, and then plus minus some, I think 2%, which means if they are equal, if the levels here are equal, what would you conclude? Can you guess what should be concluded here? I know that you have not learned this yet, but well, try to make a guess. What should be concluded here? I like you to think a lot. That's why, for example, in your lab, right, you need to explain. I will leave thing a little bit vague, but you need to explain why you make that decision. Again, I still have that. Well, I would say another. That's the next slide is the answer. But I want you to think first. Once you saw this graph, what would you conclude? What would you say about the association between marital and Y? Right. marital and the variable y, not why it happens. Why divorce is more than married. Not about the question though. I want to know the conclusion that you can make about these two variables, the marital variable and y variables. They all have the same chance. That is, but that's not the conclusion. The one that you just type is observations that you can observe that, yeah, they have about the same chance. What does it mean? What does that mean? Having the same chance. What does that mean to the relationship between two variables? Having the same chance. What does that mean? Say yes to offer no matter what their status are. Right. And another comment here, marital type is irrelevant, right? I suppose that you want to type not irrelevant to choice they make. Correct. They are not related. Put it in a simple term. They are not related because it doesn't matter, right? It doesn't matter which marital status that the customer have. The chance is about 13%. Right? So it doesn't matter. They are not related. And that leads us to so from the observation here, we can probably conclude that it doesn't, they are not relevant to one another. They are independent to one another here. And that it will lead us to the measurements that in fact you can measure the probability of yes at each category. Right? Although I write like this, but this is the probability of yes when you are considering just one row. Like this. Right? So if you take the 128 and then divided by 128 plus 5,079, this will be the probability of yes when the customer has divorce status. So what is this values? You have already learned this concept in your statistics. This is called the conditional probability. So to write it in a global term, I should write it like the probability of yes given divorce. Probability of having the one, well, this is a little bit shorthand though, because I didn't write the actual, right, the marital equal yes. So, well, let's write it in full term instead of the shorthand. So what I should write here is PR y equal yes given marital equal divorce. Right. This is the conditional probability, right, of having divorce status and then accept the offer, right, here. And this is for married and for single. Then we can compare this to the actual proportion, but I don't know yet. Right, let's look at the proportion first. If we take, say, df $y summary. Yeah, table. Then it's 5,289 divided by the total number of rows, which is 45211. So if you look at this, the chance is about 0.117. This is the probability of yes, right? Probability of y equal yes, equals 0.117. This is known as prior probability, right? Prior probability is the probability of the chance. Oh, undo because we'll switch back. It's the prior probability of yes. Prior probability, you can think about it as the probability of things happens without when you're considering it as a whole. The overall chance of this event to happen. Now, if we switch it back to this, we now see that because we know that PR, yes, equals 0.117, but this one is 0.24, right? 0.024. Oops, I think I made mistake here, possibly. Did I? Yeah, probably I. Why is the number not the same though? Probably the data is different. Oh, this is for default. Different values. I forgot to look at this. Well, I'm trying to, for this one, I'm looking at the default, means who is bankrupt or having the default status on their account. Default status means that account got, simply speaking, banned for doing transaction because the customer has not paid. So I want to know association between the two in this case. And that means, well, I should compute different prior. Right? The prior here should be the prior about the default. And that is 815. Which is 0.018. This is the prior prop for probability for default equal yes. Not y, sorry. Yeah, this is my mistake, right? Prior prop of default equal yes, equal 0.018. Then now let's compare this. I should fix this first. Not y equal yes, but should be default equal yes. And it's not this value. Erase it. 0.018. Okay. Now, when we look at this, you can see that the values of the conditional probability comparing to the value of yes here, 40 watts is a little bit more, right? 0.024, and for merit is about the same. For single, it's also about the same. But if you got the watt status, then you have higher chance to be default, to have default status. Okay. So with this, you can then determine whether they are associated with one another or not. For this one, we know that this is 0.024, right? The conditional probability. That is actually the one that I don't think I put it here. Let's see if there's here. No. You can divide them. You can divide the value of the probability of. This is something else, will not be the example, but this is one of the measurement that you can do with that. You can use probability of, say, x given y, of y given x. of y given x divided by probability of y. This measurement is called lift. Lift is the proportion between the conditional probability of the event given certain things, that is the characteristics, and divided by the prior probability. This would usually indicate the how higher chance you obtained it, right? The gain in the probability. So it means that you just take for this one 0.024 divided by 0.018, right? And should equal about 1.5, I think, or some value like that. 0.24 divided by 0.018, 1.33 equal 1.33. So this is not really exam, but I just want you to know that you can determine how high a chance you get by using these types of measurement, and there will be a number of them that allow you to measure the associations. But this is a way that you can calculate the conditional probability between two variables from the cross tabulation. Right now, you start to see relationships between what you have learned in your statistics and this class. That is actually all of the concepts that you learn in statistics is very useful in data analytics. Right? For this simple example is that the basic concept like conditional probability allow you to determine associations between variables. So if these two values would differ a lot, like this one, if it is something like 0.1 or 0.5, which differ a lot from 0.018, then it would mean that this variable, the numerical, associate with the event that you are considering. Right? But because if we now consider just this prior probability and the conditional probabilities that we have, right? 0.024, 0.016, 0.018, you can see that they are about the same. Right? That means, well, they are not really different. That means the two are not related. But how would you know? How would you exactly or make a conclusion and be sure with that conclusion that your conclusion about the two variables are correct? How would you know, right? There is the way that you can measure the certainty about relationship is to use the test statistics. Have you learned that t-test in your stat class yet? What is the topic that you are currently at in your statistics? In your statistics class? Central limit theorem or expected values, random variables? Anyone? Can you tell me that? What are the current topics that you are learning in your statistics course? Continuous distribution. All right. Something that is related to what we have learned at last time. Okay. After the midterm in your stat course, you learn about hypothesis testing, about how to make the null and alternative hypothesis and calculate the statistics to test whether the two groups are different, whether they have certain values or not. But for now, let's use this as a tools, right? So there is one types of way, one measurement that you can calculate the associations between the two variables. That method is called the chi-square, right? The chi-square statistics. Chi-square allow you to measure association by summarizing the number that you see earlier into just one variables, into just one measurements. Right? This statistic allows you to determine the relationship between two variables, which can be used to indicate independence in the variables from the cross tabulation. After you have the cross tabulation, you can then use a chi-square statistic to know statistical relationships between variables here. Okay, how do we do that? What you can do is to this is the equation that allow you to compute the chi-square statistics. For this one, we will come back here after we see some examples. You can compare, right? This is the comparison, right? The observed minus expected. This expected is like the prior probability, but in our case, it will be the prior probability of the joint distribution. Right? So you get the expected value, the value that should be. Suppose that they are not, if they are not related to one another, what should that value be? And then compare to the actual value, square them to get the difference, and then divide with expected so that you have the value in it's like you divide one factor out of this to reduce the variation. So for this one, when you sum all up, you get the difference between the observed and the expected in the chi-square statistic unit. And when you got this chi-square, then you can convert this into p-value, or the probability of the null hypothesis being false, or null hypothesis being true, which you will learn that later on in your stat class. Simply speaking here, for you to be able to easily understand is that if chi-square is large, then it means that the two are related. If the chi-square is small, then it means that the two variables are not related. So how do we do that? Let's look at some examples to determine what does it mean by having relationship and not having relationship. This is the results of a survey that you have a survey to ask whether this person agree with the question or disagree with the question, and you also ask about the gender of that person, the participant in the interviews, whether he or she is male or female. And then you can do the summarization into cross tabulation like this, so that you have 65, 25, 35, and 25. And from this, this is an example of weak relationship. It means that the gender does not really related to opinion. So how do we know this? Because if you just look at the male here, for the male, this is 35, this is 65, right? So if you look at the proportion, this is about 1 to 2, this is about 1 to 1. But if you want to summarize them as just one number to indicate relationship, how do we do that? We can then come back to this equation by computing the expected value. The expected value, that suppose that the two are not related, what should be the value? And this can be done by first compute the contingency table. So in order to get this result, when I start doing the analysis, it will be like this: M and F, and agree and disagree. So at the beginning, what I have is 65, 25, 35, and 25. And the next step is to calculate the marginal distribution. Marginal distribution is a distribution that when you marginalize, or think about the word margin, right? Margin means something that is on the rim, right? It's on the end. So we will marginalize, computing the distribution at just one variable. So for opinion here, it should be 25 plus 65. 25 plus 65 is 90. It's 60. And this will be 100. And this will be 50. Now, how do we then get the expected value if they are not related? The thing that you can do is to after you obtain the marginal distribution, you can then calculate the proportion between the cells. So for this one, it's like 100, and this is 2/3 and 1/3, right? Because male, we have 100 male participants and 50 female participants. That means 2/3 is male and 1/3 is female. So if the two variables are not related, the rate has to be the same. That means for those who agree, they should have 2/3 to be male and 1/3 to be female. And this is, so for this cell, it's like 1/3 times 90, which equals 60. And for this one is 2/3. 1/3 times 90, which is 30. That's why you see the value here. And do the same thing down here. You get 40 and 20. Okay. Now, for each of these, we will now compute the summation. And the chi-square summation would equals the observed 65 minus 60 square divided by 60 plus 25 minus 30 square divided by 30 plus 35 minus 40 square divided by 40 and plus 25 minus 20 square divided by 20. And we got the value down here. And in summation, this is 3.12. Because chi-square is quite low, and actually you can, because number of row and column here, you get degree of freedom equal 1. You will learn about degree of freedom later on in your stat, but for now, let's use just chi-square value. You got low chi-square values, mean that the two are not related. If you convert this into probability, the probability of null hypothesis that suppose that you learn later on will be about more than 0.05. 0.05, right? But for now, well, because this is low value, they are not related to one another. Now, that indicates weak relationship between the two variables. Let's move on. Now, let's look at the case of strong relationship. In the strong relationship case, when you, because this is like, again, 2/3 and 1/3, the 2/3 multiplied by here 100, you got more male coming in here, mean that male has higher chance to say agree than female, right? Female is about 25, but for male this is 25 to 25. So 100 here, if we use 2/3 to multiply 100, then you got 66.66, and this is 33.33. And then compute the difference again, then you have higher value of chi-square, which means that actually if you convert this to probability, then the value of 9 is mean that it has, well, the higher value means that it has higher relationship. Usually when you work with big data, you work with a lot of samples, the value of chi-square will be so large that it will be hard to be not related. So if it is not related, it would mean that they are really not related, like if they have value less than 10. Okay. All right, how to do the chi-square test? In order to do the chi-square test, you can put in the cross-tab, the contingency table or cross-tabulation table into the chi-sq.test. I will talk about the way that you can interpret the result later on. chi.sq.test and then table, say here df. We want to know whether marital is related to accepting yes or not. In this case, we see that the chi-square is 200 and p-value is less than 2 to the 10 2 times 10 to the minus 16, right? What does it mean? It means that because you have like because even though you see that the proportion are not that different, but with this small proportion, with a large number of occurrence, like in a 10,000, is 40,000 occurrence, and you got this difference, it would mean that this difference is a little bit persistent, that marital associate with the chance a bit, but it's associated with the chance. For this one, we would call it significantly associated with the chance of buying, the chance of accepting. But that significant might not be significant. It is significant in statistics. That means they are associated with one another, but that association might not be that much of the difference here. Right? So what does it mean? It means that with chi-square, you can now determine whether the two columns are related to one another or not by look at p-value. Right? From the chi-square, if the chi-square has a large value, then the p-value will be small. So in your stat class, you will learn that later on, that if the p-value is less than 0.05, then this is significantly different. In this case, significantly different, mean different population. If p-value or in other words, from the same distribution, if p-value is more than 0.05, that means they are, from not the same, from different distribution. More than here is from the same distribution. Which means, in our case here, right, for this one, less than 0.005 would mean that in terms of chi-square, that they are dependent or related, because not because they have p-value less than 0.005, they are related because when you look at the proportion, they are different from the expected value. That if they are related to one another in terms of the distribution here. So in our case here, it would mean that they are independent if it's more than 0.05. Or not related. Okay. Or simply speaking, if you are not looking at the p-value here, if x square or the chi-square is large value, it means that the two variables are related to one another. If the chi-square value is small value, it means that they are not related to one another. Right? Bioinformaticians use this technique to determine relationship between the genes. And then you know that our DNA has the code called the code ATCG, where you might have learned that in the biology class. And those code ATCG has been used to find association with disease. And bioinformaticians are the people who are working on identifying, say, the location in DNA that might associate with certain disease, with, let's say, cancer, diabetes, for examples. So with this chi-square technique, you can find association between certain location in DNA and the occurrence of those disease, right? So here, this is a quite powerful technique, and you can use R to simply compute that. Okay, so that is for in the case of category and category. How about if one of the variable is not a categorical variable? What if it is the continuous variable? If it is numeric, what would you do? Right. If you still want to use chi-square test and geom bar and on the cross tabulation to analyze this, the one of the way that you can do is to bin the variable first, right? You can bin the variables by using cut, right? Cut is quite powerful function that would cut our data into pieces, into category. So when you have a numeric variables, you can transform it into categorical variable using the function called cut here. If you cut the variable age into according to the breaks and then label them accordingly here. So let's try creating that. Usually when I create this, I will not write everything in one go. I will just doing it one by one. Here, mutate, right? Mutate age range. Equal cut and age. So by bank data object not found, sorry, SDF. I need to specify breaks. So here breaks. What should I do for the breaks? The breaks here, I use the vector infinity, 20, 30, 40, 50, 60, and infinity. And that's infinity, 20, 30, 40, 50, 60, and then infinity. Oh. Here. So I now got this age range as the partition of age according to the breaks that I have specified. Right. So instead of using this notation, I can change it into something like down here, which will label them differently. But well, let's leave it like this. Doesn't really matter because they are, well, they are treated as a factor. Then I'm going to assign this to df1. And afterward, I can find association table of df1 and df $sign or df1 $sign y or age group and $sign y. How come they are not the same length? Oh, age range, sorry, not age group. Age range. I see. Okay, now I got this cross tabulation tables that show the binned numerical column and in association with the variable y. Now we can determine the conditional pop, right? Conditional probability of belonging to this age group and the chance to buy. Just by scanning through the value here, you will notice something interesting that, okay, here, the chance is about 1/3. But for this one, the chance is lower to 1/6, right? This is 1, this is 5, also it's 1/6, 1/6 to 1/7. For this one is a lot lower, and then it becomes higher again at this end. That means there might be a certain associations between the age group and the and the chance to buy. So if we now then use the graph to plot, I'm not going to do this. Let's look at this again. You see that, well, if customers have age lower than 20 or more than 60, then the chance that they will accept the offer are a lot more than those that have, say, in the working age here. Okay, so now you know that if you have customers in your accounts that have age less than 20 or more than 60, then they would have higher chance to be to approach, and you should focus on them first before if and then because they will be easily converted. Okay, so that is how you can how you can analyze categorical variable versus categorical variable, and categorical variable versus numerical variable by converting numerical variable into category. Okay, so that is one of the ways that you can do. Another way that you can do is to perform t-tests and Anova analysis of variance, which I will not cover in my course here because they require a lot of basic statistical background that you need to learn in your statistic course. And also I would say the second statistic course, like the design of experiment or advanced statistical analysis, which you would learn about Anova here. This is a way that you can analyze the variable in multi-factor, and actually R also has the function to help you in that. But you need to understand the concept about z-test, t-test first, which you will learn about those in the concepts after the midterms in your statistic course. If I remember correctly, last year student also told me that you learn about Anova as well, right, after the midterm. So for this, I will leave it to the statistics, to the statistic course after the midterm, that you will learn about them. Right? For us now, let's say that you can now analyze the relationship between categorical variable with categorical variable. And you can also now analyze association between categorical variable and the numerical variable by binning them. Okay. Right. Let's take say 5 minutes. Now it's let's take 5 minutes break. We will continue at 9:45, and then we'll look at the last topic on the case that when you have numerical variable versus numerical variable, right? How can you analyze the relationship between them? Okay, I see you in 5 minutes. Okay, I will try to edit the video and upload for you as soon as possible, possibly within this morning. So you can, if you want to review it before the exam, you can do that. Okay, so let's continue, right? The last topic is on the analysis of numerical versus numerical variables, right? In terms of graphical representation of relationship, you can use Scatterplot to view association between the two variables, because by plotting each of the data here as a dot, you can now view the relationship between them, whether they are linearly correlated or whether they are like groups in the data or not. So Scatterplot will take each value here, each row, and then plot them accordingly. So each row would be represented as a dot in the Scatterplot graph. By looking at Scatterplot, you can determine the relationship between the two numeric variables. What are they, right? You can have the variables related in the positive relationship. It means that the relationship would increase and decrease at the same times. Or you can have negative relationships. A negative relationship between two variables means that when one variable increases, the other will decrease. So it kind of goes against one another. like the price in stock market, and one go up, the other go down, for example. So how to determine relationship between them, right? There are multiple ways to do that. One way that I will introduce you is invented or proposed by Carl Pearson. Right? He proposed a lot of measurements in statistics and data analysis. He is one of the he proposed the method called Pearson product moment correlation coefficient, which can be used to measure association between the two columns, two variables that we have here. Okay, how do we do that, right? The idea of measuring correlation is in the sense that you want to compute the strength and direction of relationships, right? You have two variables. You want to see if the two variables are directly associated in a positive way, in a negative way, or whether they are not related to one another. Okay, this correlation coefficient, usually we use R to denote that that correlation. For the population, sometime in your statistic, you will see you encounter this row, right? The again, the actually is the R in Greek letter, right? The row. So how do we calculate this Pearson correlation? Right, let's look at this example. Right, if we have a pair of data in observation x1, y1, x2, y2 to xn, yn, well, we will say that these two are in positive relationship if large X pair with large Y and small x pair with small y. So in a picture here, means that large X pair with large Y. This is X, this is Y. Large X pair with large Y. And small x pair with small y. And so you have an association that looks like it as a line going up. If they are in negative relationship, then your x and y would look like this. You have the small y, the large X pair with small y, and small x pair with large y. And that means it will go down here. If your graph looks like a line with negative trend, that should indicate negative relationship. How about no relationship? In no relationship, you may have a graph that looks like this, spread all apart. There's no relationship between them. And there are plenty more, which I will show you later on. Okay, so large X pair with large Y, positive. Small x pair with small y, negative. How do we measure? How do we convert from those ideas into mathematics, right? Pearson proposed that you can use the covariance. You can use SXY to compute that value. So if in positive case, X is large, Y is large, and X is small, Y is small. In that case, the xi minus x bar, if X is large and we compare it to means, this value would be positive value. And yi minus y bar, if y is large because it's large and large, right? Y is large is more than mean, then it will also be a positive value. Then the SXY for I should choose SXYI for a specific I in this value will be positive value because when you multiply positive with positive, you get positive value, right? With small and small, you get minus and minus multiplied together, you get a plus value. So it means that if the data is in positive relationship, you would have the value of SXY in each term of I more than 0, okay? But in the negative relationship, you get a large X paired with a small y and a small x paired with a large y. A large x means large x, if we subtract the mean out, you get positive value and negative, negative and positive. Multiply them, you get negative values. And that means if your data exhibit negative relationships between x and y, then each term of the multiplication would tend toward negative values. Okay, once you sum them all, this value will indicate whether the data have the tendency toward positive relationship, negative relationship, or no relationship. No relationship can occur if you have like positive mixed with negative, and there is no relationship between them. Okay. This value will tell us, right, if they are more than 0, then it will tell us that this is positive. If they are less than 0, it will tell us that this is negative. So by combining them, it will allow us to determine associations. However, right, just this value alone doesn't give us the clue of the strength. Indeed, it gives us that that the variables are associated, that the variables may have relationships in positive or negative way. But it doesn't tell us whether that relationship is significant, whether that relationship has high magnitude or low magnitude, right? Whether that relationship is a strong relationship or a weak relationship. Right? To determine that, we need something to compare with, and that thing is the size of the vector. We use the size of the variation, right, to divide them. Right? So now once we have this is like the sum of the difference between the value to the mean of x and y, right? Dividing them, this allows us to conveniently compute the value, because although it looks complicated in mathematical sense, but once we multiply the terms, right, xi multiply yi, x bar multiply y bar, and do the same thing, and then down here as well, we got a more convenient form here, that is n summation of xi yi minus summation of xi summation of yi, and here, and this is n summation xi square and summation xi square, right, and then for y as well. And this allows us to compute the relationship between the two. So let's see. Let's look at some example here on the calculation of correlation. I'm going to share the dash. Let me share this as whiteboard. Okay. So for this one, I'm going to start with the data that we're supposed to have. Let's say we have 5 points between x and y. We have 1 and 1, 1 and 3, 2 and 3, and 3 and 5, 4 and 4, and 3 and 3 then. I suppose we have these 5 points. Yeah, I suppose we have these 5 points. We are now calculating the Pearson's correlation. So I'm going to use the equation here, equals n and sigma xi yi minus sigma xi sigma yi divided by square root of n and summation of xi square minus summation of xi square. And here, and summation of yi square minus summation of yi square. Right, now let's do the calculation here. I will start with writing this table x 1 2 3 4 3 and y 1 2 1 3 5 4 3. Well, when you use computer, it actually do this automatically. But I would like you to show you that it is really convenient to use this equation, because whenever you see the equation that got like summation of x, summation of y in terms of data, it means that you just need to sum them, right? And that means it's easy, right? But when you have a lot of unknown variable inside, that is the problem, right? And you need to use something like optimization to help you in that case. But this formula is very easy. Just needs to follow here. So what do we need? We need to have x squared. If you look at equation, we need to have the summation of x, summation of y, right? So let's draw it here, down here. So this is a summation. Summation of x is 13. 6, 10, 13. Summation of y is 6, 10, 16. Right, and then what do we need? We need x squared and y squared. And y squared. X squared is 1, 4, 9, 16, 9. Y squared is 1, 9, 25, 16, 9. And then summation of x squared and y squared is 10, 26, 20, 39. And that one is 10, this is 25, 50, 60. Okay, and x times y. One, 6, 15, 16, and 9. And sum them up. This is 22, 32, 37, 47. Is that all? Yes. Oops. Yeah. That's it. Then we need to compute R. R would equals 5 times 47 minus summation of x 13, summation of y 16, divided by square root of 5 times summation of x squared 39 minus summation of x and square minus 13 times 13, and multiply with 5 times 60 minus 16 times 16. Right, so this is the value that we need to compute. Let me use a calculator. Actually, I'm going to use R to help me calculating this one. 5 times 47 minus 13 times 16 in parentheses divided by parenthesis 5 times 39 minus 13 times 13 multiply parenthesis 5 times 60 minus 16 times 16. I'm just think about using calculator. It's the same thing here. Okay, did I make mistake anywhere? 5 times 47. Oh, square root, right? square root. SQRT. Forgot to use square root in R. Ah, 5 times 39, not 29. Okay, so I got the value of 0.79 for this one. 0.79 indicate actually strong and positive relationship between the two variables. I mean x and y are in positive relationships. Let me capture the screen for the afternoon session as well. How do I do that here? Annotation, screen capture. Okay. Right. So this is how you can compute correlation between the two variables. Right, and the values in that you obtained it from computation will indicate the strength of the relationship. In fact, if you look at the magnitude alone, the values of the correlation relate to the variation of data. If your data has like no variations in terms of the trends, that it has just the trend without any variations, you have high value of R, like R equal 1. R equal 1 means that you have no variation in the trend at all. But if your R is lower, it means that your data are kind of farther spread apart, like 0.9 here, it's a little bit spread apart here, but at 0.5, you just got a general trends. It also indicates the certainty of the relationship. For this one, you can see that X increase always contribute to Y increase. But when you have, say, R equal minus 0.5, when X increase, this between, let's say, compare between the 2 points that I point out here. When X increase, it doesn't mean that Y has to decrease, right? Sometimes when you increase X, it even increase Y, which in this case it shouldn't be, right? It has negative relationship, but because of the variations, it can happen, right? So the lower value means the less certainty that you can obtain from these measurements in terms of the relationship between the two variables. The range of correlation ranged from -1 to 1, right? From having negative relationship to positive relationships. If you have strong relationship, the value close to 1, strong positive close to 1, strong negative close to -1, and no relationship, the value would be about 0. So how much is high, how much is low, what is strong, what is weak? So what is the threshold to determine whether this is a strong relationship or this is a weak relationship? Right? There is actually no exact rule of thumbs or no exact rules that should be used. It's not like that this is the rule that you should obey. It can be different from this one depending on the data that you are handling, right? In one of my research, right, I even use a strong relationship to have threshold about 0.7, not 0.8. Right? 0.8 is a bit too high for that data set, so I lower a threshold a bit to about 0.7. For the week, I also decrease the threshold here to say 0.3. So these are adjustable. As long as you have a strong relationship at the high end, weak relationship at the low end, and the middle are the moderate relationship, the medium relationship that you can obtain. And this is in absolute value of R, right? It doesn't mean that -1 is weak relationship. No, it doesn't mean that. -1 is also strong relationship in negative direction, okay? Because it depends on the shapes of the distribution. If you have the shapes like this one, you got like correlation equal 1, no variation at all. It is quite certain that it happens. But when you have higher variations to the point that there's no trend at all, variation wins out, then you got zero correlation. In this case, a little bit toward the negative and also -1 here. And there are also an exception here that if there is no relationship between the two variables, it means that when one variable change, the other variable stay constant, right? Stay constant. This also indicate no correlation between them, right? Zero correlation. So having correlation equal 1 doesn't mean that you get the slope differ, right? The slope may not be the same, even though you get the same correlations. It just tells you that they are associated. It doesn't tell you that they are associating with one another a lot, or whether changing one variable will contribute to a large value. It doesn't tell that in this case, right? It doesn't contain those information to tell you this story, right? Correlation is good in measuring associations. So high value indicating that they are associated. If you want to know how much they are associated, you should use the thing that you will learn later on after the midterm, linear regression, to determine the slope in that you can obtain it from this scatter plot. Also, correlation can measure linear relationship. If relationships are not linear, but there are some like this one, sinusoidal, right? Correlation would not be able to measure such a weird shape, right? You might need to use other things like polynomial regression and others, but those are hard to conclude in terms of decisively conclude that they are related to one another or not. Or if you have the data in clusters, right? This is also bad for correlation. Correlation has this assumption that you have like just one, doesn't explicitly tell in the text, but it inherently assumes that you have one populations. And because you are measuring comparing to just one mean, it means that you have just one populations. But if you have multiple population containing in the data, then correlation might fail you. Or if your data is associated in a varying manner here, correlation wouldn't help, wouldn't tell you that there are something interesting here. Okay, but yeah, if you find the data that looks like this, there's definitely something interesting here. Okay, this shape downward here. Okay, lastly, as a critiques of comparing CO2 with temperature, correlation is not causation, although they might be related, right? When you have correlations between the two variables, the null hypothesis of this is not that it doesn't tell you that one variable associating cause the other variable. It just tells you that they are related, right? So correlation between two variables might be that, okay, there is a cause effect between x and y, or there might be a reverse cause effect between y and x. That is possible. Or there might be like a third one, right? A third one that is related to both, that cause both to change. Or there might be a complex interrelationship among variables and other variables as well, and not just the 3 or the 2 that you are considering. This might be just the end result. Or the last thing is that the relationship might be coincidental, means that they are just happen by accident. It is possible that it is a coincidence that your experiment might show that they are related, but in fact they are just chance, because when author repeat your work, it might not be the same. Okay, so these are the possible explanation. So keep that in mind. But having good relationship, good correlation is great, right? If you can determine variables that are correlated with the target variable that you want, then it is a good sign that you have an indicator for prediction model that you will learn after the midterm. Okay, how do we determine correlation in the data set? I'm going to use the data MT cars and show you that. So in the MT cars, let's load the data MT cars. This is MT cars. This data contains the car specification that each row indicate each type, each model, each car model, and there are measurements in columns. So what I'm going to do is to compute correlation so that I would know correlation between row, so that I would know that this model is close to which models. Or I can also determine which variables is associated with which variable. So you can do it row-wise or column-wise. Right? So what I'm going to do is to do column-wise to determine, because if what if I'm going to predict the MPG, given the spec I want to know before test drive or before testing it, whether this car would have like high energy efficiencies or low energy efficiencies before that. So how do we do that? What I'm going to do is to use let's compute directly MPG and WT here. So I'm going to switch here. There's the function core allow you to compute Pearson correlation. So I'm going to compute the Pearson correlation of MT cars $sign MPG and MT cars $sign WT, the weight of the cars. And correlation between the two indicate that they are negatively correlated at the magnitude of 0.87, 0.86. This is quite large, means that this is quite certain. So if we plot the graph between them, the ggplot MT cars and say aesthetic of x equal WT and y equal MPG and plus geom point. Now you can observe the negative relationship between them, and if I add the geom smooth and method equal LM, then I got this approximation, linear approximation of data to determine that, okay, you can see that they are quite linear, yeah, although there are some outliers here. And this is the drawback of correlation, that once it has outlier, it might distort relationship a bit, because from the general data here, you can see that the trend is a little bit steeper than that. But with this data point, a low efficiency, it kind of draw the conclusion out. But in any case, this is correlation. So correlation is affected by outliers. Okay, you can also compute the pairwise correlation, a correlation of all columns by using core and the data frame that you want to compute correlation here. So this is MPG versus MPG has correlation equal 1. MPG and horsepower minus 0.77 with the weight is 0.77 with something else with the rad or cubic here or VS here is positive side. Okay, so this is a way that you can use core to plot to determine correlation, and this I can assign to the result. And then you can use, this is a cool package called core plot. Core plot allow you to plot correlation in this graph. In this graph, in core plot I specify that I want it upper here. You can use lower as well. And then I ask it to order order this by hierarchical clustering. Hierarchical clustering is a technique that you can group the data, group the column together if they have high value of correlation, if they are similar. So they will be grouped together here. So that's why you see the red and the blue gather together in one another. So for this one, I will know that these are the group that are positively correlated with one another. These are the group that negatively correlated with one another. And the last two here, I don't remember. You can look at the manual yourself here. So the core plot allows you to plot the correlation, the representation, the visualization of the correlation between the graph. For this one, you will know that, say, MPG here. MPG is negatively correlated with these four variables, with the weight, the horsepower, cylinder, and displacement, the size of the car. And MPG is positively correlated with these two variables, with AM, right? Whether your car is automatic or manual gear, and here, VS, I don't remember. If you can help type hell and empty cars to look at that, right? Here, so this is the way that you can display the correlation plot in R. Another way is to use the heat map, right? Use the heat map and do something actually similar to that one, but a little bit harder to see though. For this one, I use the function called heat map and use the result X, and then say column is the is call here, and this is the, this is not column, sorry, this is color. Like color will be green, black, and red. 20 color ramp palette. Color ramp palette will generate the range of color from the color scale that you give it. This is green to black to red, 20 scale. And then give it here, and then say symmetry equal true, and then you get this result in the heat map. Although I would say that this one is easier to interpret though, but this is the way that people do correlation back then in when I was a researcher in bioinformatics, and they usually display this graph. So it's a little bit symmetric, but because it is a square, I think it might be easier to print in the paper, in the research paper. But this one is also good because it just tells you that which variable associating with which variables. Try to play with both though. You can, for either correlation plot or correlation heat map, they are both useful. I supervise a project for, I was a consultant to a big telecom company, and once and they invited me to a meeting that they have a foreign company, consultants from abroad to do the project for them. And at that meeting, what the consultants also show the graph like this one when they do the job, that they have to perform correlation analysis of the variables to determine which variable correlate or associate with which variable, particularly focusing on the Y variable, the target variable here. So this is a standard method that has been used by consultant company, by the company that work on data science, big data, right, to analyze this correlation analysis. And you can definitely do the plot. I already did that for you to plot the relationship between the two. This is the graph of negative relationship. This is a graph of positive relationship that you have both a variable that one go up, the other also go up as well. This is for HP and DSP. And when you have no relationship, the scatter plot would look like no patterns. Okay. Well, you can plot association when you have more than two-dimensional data, but because of human cognition, when you look at the graph like this one, it is hard to comprehend when you have more than one variable at the same time. So this is also the geom bin 2D. Geom bin 2D, if you remember, would uh, would have two variables and then bin the variables, right? It would bin the variables, bin the age by 10 bin, and then plot it and then count them so that you see the distribution between the two. But this is hard to determine though. I would suggest that if you want to show relationship between the two variables like this one, use the field bar chart, like field stack bar chart instead of this. Although it is quite the geom bin 2D is quite fanciful, but it is hard to interpret. The idea of visualization is that you should create visualization in such a way that it is easy to understand while conveying the thing that you want to convey. Right. So basically, use simple statement. To convey the same information that you want to convey in this. It is quite a pity though. Usually this lecture will be on about the week of the Valentine week, right? And it is great to use to play some joke on well, I teach about relationship mathematically on Valentine, right? So yeah, but well, it is a pity that we have like Chinese New Year's and have Maka Bucha for both. But never mind that, still okay. Still in February, no, it's in March already, right? And it's the week before the midterm as well. So I'm quite cruel to give you this open lab, but well, because you have my should we or shouldn't we? Right. On the one hand, it is good to have practice, but I know that you might have a lot to do because of my course and the other course. So scratch that, right? So there will be no lab today. I understand you guys. And so no lab today. Congratulations. Right. Now it's time to prepare for the midterm exam. Right. So any questions about today's lecture? Right. If you have questions about the exam, the lectures, or anything that are related to the thing that you have learned before the midterm, ask us before the exam, which is on the 8th already. So it will be the Monday, right? Right. It will be on this Monday. So I will post it. So I have about 3 hours before the next class. So I will encode the video and then upload for you before the afternoon. So if you want to review this video, you can do so later on. All right. So let's call it a day, and hope that I wish that you all have a good luck in the exams. We use class marker. So how many lectures will be covered in the exam? All of them before the midterm. Okay. So I wish you a good luck before the exam. Because we use class marker for the exams, I wish that you guys would be honest and there will be no cheating. Right? There will be no it should come from your abilities. Right? I can tell you that I'm already 40 something already. So the thing that you do in the past will haunt you in the futures. So do things honestly, and then you sleep well for the rest of your life. This is not like a threat, but it is the same thing. And my course is like just a little, just a thing that you will pass on, and then you learn something from this course. So do not, please don't cheat. And I have certain countermeasures that I use in the exam anyway. So you see that in the class markers. I will post the link about 1 day before the exams, so you can expect that on maybe on Sunday, but you will not be able to access the exam until the allotted time, until the 9 a.m. of the 8th of March. And you can access that up to the 9:30 only. So you cannot miss that, all right? It is same as going to the exam at the university, but you need to do the exam online. And that's it, I think. There are quite a lot of things to do in that exam. So if you do not, if you are distracted, because I would suggest that you prepare some papers for taking notes, for calculation. Having a calculator in hand would be nice. If you ask me whether you need to use computer to write the code, you don't need them actually, and it will slow you down a lot. Just like when you do the exam in class in data camp, if you search Google while doing exam in data camp, in the evaluation, you will not have enough time to do that, right? So manage your time well, and then it will be fine. Okay, that should be about it. Yeah, I will after this I will convert the video and then upload it for you, right? So see you guys after the midterms. Okay, for today, have a good day.